This is kind of unusual format for OARC. It's a little bit experimental, so please bear with us. The following session will have 5 talks from 5 different speakers. Each speaker has 10 minutes to deliver the talk, and then we will have shared common 20 minutes for discussion among the speakers and of course you. So it will be a discussion panel. The speakers at the end will be sitting here in the chairs. I will be passing the mic around. And of course you can use the mics in the room to ask in person, or you can ask on the Mattermost. That's mostly important for the people who are remote. If you want to ask a question remotely, please go to the workshops channel and type in your question into the Mattermost message field, and please, please, please prefix it with the hashtag questions, plural, because that allows us to filter the messages in the channel so we don't miss anything in it and we can actually see what you are asking. And with that, I'm very happy to have 5 speakers who will speak on the topic of the protocol level security issues which impact the real operations. First speaker will be Richard Meeus by Akamai, and then we will follow with academic participants who in recent years discovered special ways how to misuse the DNS to attack DNS itself or other systems as well. So Richard, the floor is yours.
Thanks, Petr. So if this is an experiment, I guess this makes me the first guinea pig. So thank you very much indeed for letting me talk here today. I just want to share some facts and figures from Akamai around DDoS and specifically DNS's role in that. Akamai has a number of authoritative DNS, recursive DNS, and DDoS platforms, and this data is taken from a number of those different solutions. The first one is DNS is prevalent in a lot of DDoS attacks. It is either prevalent in the DDoS attacks as a vector, as in reflection attacks, which I think we're going to hear more from later, but it's also a target as well. So we call those resource exhaustion attacks when it's a target. And when DNS is used as an attack vector, we call that a reflection attack. And you can see that within the last few quarters, we've been seeing 65% of DDoS attacks have leveraged DNS in some way. So let's go and have a look at what those 2 factors are. I know most of you are pretty much experts on this sort of stuff, but just as a clarification, the difference between, on the first one, a reflection attack. Now, reflection attacks are common across all sorts of UDP-related internet services. So if you think DNS, you think Network Time Protocol, NTP, Simple Service Discovery Protocol, SSDP, Memcached, all of these were UDP services. And because they're UDP services on the open internet, very easy to launch a reflection attack. Reflection attack is when you get the target IP address, you spoof that, you send a request to a target, in this case an open DNS resolver, and that responds back, not quite sure that wasn't me, it responds back to the target. So the idea here is that you can do a small request to the resolver will come back with a large payload. And depending on how you pad out the DNS files within the text files, you can create very large responses, sometimes 10, 100 times the payload to request amplification. So not only does this generate huge DDoS attacks, sometimes hundreds of gigabits per second, it's also very effective, very cheap to run from the attacker's perspective. The other target is what's called an NX domain attack. It's also called a pseudo-random subdomain attack, also known as water torture. This is when the previous one we were looking at, that was targeting any internet asset. Previously, when we were talking about using DNS as the attack tool, that's attacking any web asset, could be a website, could be an API gateway, could be a VPN endpoint. In this case, DNS is the target. So what we're doing here is saying that Okay, well, when we want to resolve a normal domain name, it's very simple. We just go up to our local resolver. That could be an RISP, or it could be, quad 8 or a quad 1 or something like that, and that's going to resolve that IP address, and that's going to cache any known domain names. The problem is with the solution with that is if you put a random subdomain in front of it. So if I go to www.akamai.com, that's going to be cached in the local resolver. So I don't have to go through to the authoritative DNS. However, if I go to abc123.akamai.com, that's a unique domain name. So that's going to have to go, that won't be cached, there won't be a positive cache for that. So that's going to go straight through to the authoritative domain. So if I do abc123.4, that's another unique domain name. .akamai.com, that's another unique domain name. That has to go through to the authoritative resolver. I then have tools that generate thousands and thousands and hundreds of thousands of these unique domain names, spread that across a load of bots, and I can generate tens of thousands of requests per second that bypass the cache in all those resolvers, and it goes straight to my target DNS server. Now, if I get hit by all of those individual attacks, my DNS server might not be scoped out to deliver that many queries per second. It overloads, and then the TTLs will expire on the recursive DNS servers, and now none of our legitimate requests can get resolved. As we know, no DNS resolution, everything breaks, bad things happen. So along with that, we also see an increase in the number of packet per second attack as a whole within DDoS. So we can see now we've seen an exponential rise in the packets per second attacks. And I wanted to bring in this one, which is the attacks are getting longer. This is using other tools as well, not just DNS, but other vectors as well. But we can see now that the duration of attacks now has gone from what we were seeing back in sort of 2018, about 7 minutes, going up to double that. And that's mainly now to try and prove a point. The reason being is that 6 years ago, attacks were mainly around ransomware, DDoS for ransom, that sort of thing. Now we're seeing a lot more hacktivism, especially in Europe. We're seeing a lot of hacktivist-based attacks due to the fact we've got a number of conflicts going on in the region. Therefore, more persistent attacks from the hacktivists is becoming a relatively common trait. So this is just an example of what can happen when we get that water torture, that PRSD style attack. This is a major sports league based out of the US, and you can sort of see the number of requests on the right-hand side, but the arrow is pointing to what we're getting for the NX domain percentage. So this is the number of random subdomains that are being put through to the authoritative DNS server. And that's running at 76.8%. I did a query for a customer yesterday on a normal day. They're normally getting like sub 1% of NX domains, normally a fraction of 1%. So 76.8 is way, way, way in excess of what we would normally expect to see. When we look at the actual amounts of requests that are coming through, if you look at right at the bottom on the left-hand side in the purple, that's what they normally get. So that's about sort of 1,000 requests per second. It's peaking at about 95,000 requests per second. That's a factor of 100. Now, that's not a huge amount. I mean, I know a lot of you probably have ISP-based services where you're hosting millions of requests per second. But if you're scoped out as an individual company or an enterprise to scope 1,000 requests per second, and then you suddenly get hit by something that's 1,000 times greater, you haven't scoped that out. You haven't got the scaling in process to be able to do that. And if you look at the duration of that attack on the bottom, this wasn't for a couple of minutes or a couple of hours. This was 10 days. This was a 10-day long attack that peaked in that 100,000 requests per second. So this is where we need to sort of think about scaling out that architecture at the back end as well. So when we look across our authoritative domain infrastructure as a whole, the numbers on the left on the Y chart are in billions per week that we're seeing. So this is the number of authoritative requests we're seeing per week. So we're seeing about, say, back in 2nd of April this year, we were seeing 100 billion requests. 30% of those were an X domain across our authoritative domain. So there's a huge, this is seen as a primary attack vector to take down authoritative DNS. We're now seeing, if you go to the right, 18th of June, we were seeing up to 40% of all the requests coming in were seen as NX domain. Not across all customers, but across certain customers where they're specifically targeting them to try and bring down their authoritative DNS. So this is seen as a major attack vector. And when we look at the verticals that are primarily affected by these sort of attacks, financial services is often seen as one of the primary ones. If we look at DDoS attacks in Europe, DDoS, EMEA is the most attacked geography, and financial services is the most attacked vertical. And authoritative DNS through the PARSD, so the random subdomain attack, is the most prolific attack vector. So in terms of mitigation and protection, you really look at the scaling capacities of your authoritative DNS. Do you have that capacity to scale that out? If not, you want to be looking at what are the traditional DDoS defenses you can put in place for that, whether it's hardware, whether it's cloud-based services, but also look at the potential for putting in authoritative proxies in front of your authoritative DNS services that can have a bit more scale to absorb a lot more of that traffic and understand if the requests are coming in from malicious entities or they're behaving in a way that would be considered abnormal and would have sort of pseudo-random subdomain tendencies. With that, I think I'm done with 4 seconds to spare, so thank you very much indeed, and I'd like to hand back to Petr.
Thank you very much, Richard. The next speaker was supposed to be remote, but he, for scheduling reasons, couldn't make it, so we have a recording of his talk, and the questions will be handled by his colleague or then colleague afterwards. So please, if you can start the recording. It's Xiang on the topic of DNS-Bomb.
Xiang from Nankai University. So in this talk, DNS-Bomb, a new practical and powerful podding DOS attack exploiting DNS queries and responses, we introduce a new podding DOS attack. So before the details for the attack impact, our DNS-Bomb attack could be exploited to DOS arbitrary targets with podding traffic. The bandwidth amplification factor could be over 20,000. So in the following, I will introduce how it works. So DNS plays an important role translating domain names to IP addresses and providing a solid basis for multiple applications and services. So since DNS is the cornerstone of the Internet, attackers have long been attempting to carry out traffic amplification attacks through DNS. So there are 2 ways to amplify traffic, including bandwidth amplification and packet amplification. So after it was proposed, new attacks have long been developed. However, traffic amplification in the traditional way could be easily detected by the amount of traffic. Researchers have proposed a new amplification attack with a hard-to-detect podding traffic. So, by concentrating a low-bandwidth traffic into a high-bandwidth podding, the attack is hard to detect and can induce packet losses. So, however, previous podding DOS attacks could only yield a low bandwidth factor or require large pause period. They are not practical and powerful enough. Then in this paper, we observed the capacity of the DNS resolver to concentrate traffic had never been studied in depth. Then we designed and proposed a new brand of podding DOS attack based on DNS and named it as DNS-Bomb. So by exploiting 3 inherent DNS mechanisms to DOS, we translate the defense into some attack factors, including the timeout, query aggregation, and response fast returning mechanisms. So the basic idea is like the Kamehameha in a cartoon Dragon Ball. We turn the DNS traffic into a blast wave. So the threat model of DNSBomb is shown here. In step 1, Kami, we accumulate the DNS queries using the DNS resolution time-bottom mechanism. So during the query timeout, the attacker then just send many queries into the target resolver and hold the responses on the authoritative name server side. Then the resolver can never get a valid response and can accept new queries. Then in step 2, Hami, we amplify DNS queries into responses using the DNS query aggregation mechanism. Because for a same queue name, the recursive resolvers will only send one outgoing queries into the authoritative name server, which will reduce the overload of the attack. Then in step 3, HAR, we concentrate the DNS responses into the victim side using the DNS response fast returning mechanism. So before the timeout, we attackers can, on the authoritative name server side, return a valid response to the recursive resolver. Then after receiving it, the resolver will send responses to all the queries in the meantime. Then the low bandwidth query traffic is concentrated to a high bandwidth podding traffic into the target server. Then the attack can achieve a high bandwidth M factor. So by testing 10 mainstream DNS software, we test the attack factors such as timeout, packet size, and returning time. So after local small experiments, we demonstrated the effectiveness and huge impact of DNSBomb attacks. So for example, using the unbound software, we can achieve a bandwidth amplification factor of over 20,000. And the victim side bandwidth is about 2.9 Gbps. And these figures on the right show the huge podding traffic with a red podding, which demonstrates the effectiveness of DNSBomb to concentrate the traffic. We also tested 46 public DNS resolve services and found all of them could be exploited to conduct the powerful DNSBomb attack. And among them, 14 out of these 46 services could bring a BAF over 1,000. And the table on the right shows a part of vendors with a huge impact. And the right red period shows the podding traffic, while the green part is a low bandwidth query traffic. To find vulnerable open resolvers, we employ 2 ways to expose the population. So first, by scanning the internet, we use Akamai and the SPDS to identify the software vendor and found over 28% of 1.8 million resolver software versions which are vulnerable. Second, by designing measurement tasks, we measure the attack factors of 1.8 million resolvers, and we can only use some canned payloads and not to conduct the real attacks. We find that over 50% resolvers could accumulate 1 key queries and support timeout over 1 second, and support packet size of over 1,000 bytes. All of them could be exploited to conduct the DNS-bomb attack and induce a huge amplification factor. Besides, we try to figure out how DNS-bomb affect the real-world amplification. We use unbound and send-to-10 queries with a timeout window of 10 seconds, and we found that the network bandwidth could be totally occupied, and the DNS resolver never received a query, and the H2 services cannot be fetched. However, H3 is not much affected. So since DNS-bomb is such powerful and practical, and we proposed the mitigation solution to defend against it. We suggest limiting the attack factors, including timeout with limit, packet size, and response return time. And by conducting experiments, we provide detailed mitigation results and found restricting the timeout and response returning time has the best effort. And some of the mitigation solutions have been designed and developed, such as Unbound. So as disclosure, we report DNS-bomb to the DNS community and all DNS vendors. They have confirmed it and is implementing solutions to fix it. 10 CVE numbers and 1 industry-wide CVE number are assigned. All DNS implementations, including bind, unbound, and public services such as 1DNS, Quad 9, 10 DNS are effective. So this is my share today. Thank you all for your attention.
Thank you, Xiang, even though you cannot hear us. And the next speaker will be I apologize, Duan from ETH Zurich on the topic of basically combining multiple attacks together to create one incredible.
All right, so thanks for the introduction. So I'm going to talk about our research on analyzing a large class of denial of service vulnerabilities in DNS. And this is joint work with several colleagues from ETH Zurich and Alma Swiss. The primary focus of our research group is actually on building secure communication systems. So for the analysis of DNS, we have also followed a constructive and systematic approach with the goal of identifying the essence of problem and fixing them in fundamental ways. In the past few years, we have seen the emergence of a stream of denial of service attacks on DNS, and many of them share the same trait that each single request from the from the attacker can cause a resolver to generate a number of queries while interacting with maliciously configured name servers. In other words, these attacks can produce a very large message amplification factor, and also they usually target DNS servers themselves, right? And so therefore, we call this kind of attacks self-amplification to distinguish them from conventional reflective amplification attacks. The possibility of self-amplification has actually been very long predicted by the designer of DNS. It's already very clearly stated in the canonical RFC for DNS that resolvers should bound the amount of work during resolution, right? And from it also gives hints at how things could go wrong, like for example, a resolver getting into infinite loop. So from a security perspective, so this clearly indicates some sort of denial of service vulnerabilities, right? And given the complexity of DNS, I guess many of us would like to ask how many such vulnerabilities exist and how large can the amplification factor be? And we'll try to answer these questions by first establishing a taxonomy of what we call amplification primitives that are inherent in DNS protocols. And based on that, we analyzed how these primitives can be combined, and this allows us to discover a whole family of vulnerabilities that we call CAM, and which can multiply the amplification effect of individual primitives. And to build such a taxonomy, the first question we ask is, what are the atomic forms of amplification? Right? During an amplified resolution process, a resolver will send a set of queries, and we call the initial query name as a base and subsequent names as derivatives. And then we can look at how these names relate to each other. As the first criterion, we consider whether the names contain each other. Right? At one extreme, all the names are on the same part of the DNS hierarchy, which means they must be resolved in a strict top-down manner. And some of them may be queried multiple times. So we call this form of amplification self-probing. At the other extreme, all the names are on separate parts, so they do not contain each other. And we further distinguish two cases here. First, all the names, all the derivatives are independently queryable, which means they can be resolved in parallel. And we call this form fan-out, which extends the breadth of the resolution. And next, each derivative uniquely depends on another, and they must be resolved in order. And we call this form chaining, which extends the depth of resolution. So what's nice about this classification is now we can break down any complex resolution process into the three atomic forms, right? But before that, we must know how each of them can be realized. There are two possible ways to realize self-probing. The first, query name minimization, can generate excessive queries for a deep name with many labels. And the other one, what we call dense delegation, creates delegation at each label of a deep name, and therefore can trigger a very long iterative resolution process. For fan-out, we generalize the technique or the kind of NS fetching mechanism exploited by NS attack and make it effective even for resolvers that have been patched. And for chaining, we also identify two primitives, the referral chain using NS records and the rewrite chain using CNAME or DNAME record, each with multiple variants. So we ended up with 5 distinct primitives, all based on common DNS features. And the taxonomy, of course, can be extended further as new features are introduced. And for example, the latest service binding mechanism. But what's more interesting is to see how these primitives can be composed. And here, the key idea is that one primitive's derivative can initiate another primitive. And we call them primary and secondary, respectively. And we focus on compositions that are regular and multiplicative, meaning that all derivatives of the primary will initiate a secondary of the same size and type. It's also possible to have additive or irregular compositions, but they are very easy to construct once we figure out the composability results. So in theory, there are 25 ways to compose the 5 primitives, including composing a primitive with it itself. And out of them, we identified 16 compositions that satisfy our regularity and multiplicity constraint. And all of them are actually based on legitimate DNS features, except 2 of them that create alias for name-server names, which is prohibited by one of the RC. But we find this is actually a little bit controversial in practice because many resolvers still allow these compositions. So we have also figured out how to construct these compositions with carefully defined zone files. And this is one example with rewrite chain composed with fan-out using 2 name servers. And I guess because of the time limit, I won't go into details, but if you're interested, please read our research papers. They are full of details. And now, with this composability result, what else can we do? Well, we can go beyond 2 dimensions, right? So here's an example of three-dimensional compositions where each primitive of the primary fan-out initiate a secondary primitive, chain primitive, and each derivative of a chain initiate tertiary self-probing primitive. As you can imagine, there are exponentially many multi-dimensional compositions, right? So this would allow us to actually explore the behavior of a resolver and push its amplification limit really to the limit. So I'd like to very briefly discuss our evaluation of the compositions on early versions of bind and unbound. So first off, both resolvers set very reasonable limits for individual amplification primitives. And but after we combine these primitives, you can see very clear amplification effect right? For bind, when we compose in a rewrite chain with fan out, we get a math of over 200. And for unbound, when we compose in dense delegation with a rewrite chain, we get a factor of 1,000. And if we extend the compositions to a third dimensions, and we'll get even larger numbers, right? And because the entire thing is further amplified, multiplied. So of course, both resolvers have been effectively patched, and now their achievable amplification factor has been much, much lower. So just to quickly wrap up, as we have seen that the issue of self-amplification are actually deeply rooted in the design of DNS, and they cannot be eliminated. And we really hope our methodology and findings can help the community better understand and mitigate these issues. And regarding mitigation, one best practice is to always set an overall limit on the number of queries resolvers sent for each client request, and because this effectively upper bounds the amplification capability of the resolver. In the long run, we believe it's very important to resolve ambiguities in RFCs or in the DNS protocol specifications, especially those leading up to denial of service vulnerabilities. And it's also very important to provide more explicit guidelines on how to proactively mitigate those issues. So with that, I'd like to just stop here and thank you very much for your attention.
Thank you very much. Because attacking just the network is not enough, the next presenter will be Elias Heftrig, who will be presenting an attack targeting the CPU. The floor is yours.
Okay, thank you for the introduction, Peter. As you said, my name is Elias Heftrig, and I'll present long-term solutions to KeyTrap vulnerabilities, which is based on a talk we had earlier on a publication at ANRW this year. First, I'll give you a recap on KeyTrap, followed by issues with the short-term mitigations which have been implemented to counter KeyTrap, which do work, but have their shortcomings as long-term solutions, which will I propose then as the third point. So, KeyTrap was a denial of service attack on DNSSEC validators. We had a very high impact. We were able to achieve stalling of resolvers of up to 16 hours in the lab with just a single response. The attack required ridiculously little resources, and all the tested DNSSEC implementations were found vulnerable. Not only resolvers, but also libraries, zone file checkers, debugging software, you name it. And to be precise, up to date, we are unaware of a single implementation which was not vulnerable, which also translates to a large number of vulnerable networks. And in consequence, patching against KeyTrap requires very tight coordination with a multi-vendor task force across the industry, some of which are here today, I've seen already. To remind you, this was the highest impact attack vector, which is KeyTrap is known for. This exploits requirements the DNSSEC specification, namely that the resolver has to try all possible keys for a signature until one works, or it runs out of keys. And also that the resolver has to try all possible signatures for a record set until one works, or it runs out of signatures. Combine that, and you get a pretty impactful CPU resource exhaustion attack at the validator. Yes, this was one attack vector, but due to the openness of DNS and DNSSEC, the protocol semantics actually allow for large number, uncountable number of KeyTrap-like attack vectors. We presented a number of them in our works. For instance, you could also exploit DS hashing instead of signature validation, or use valid signatures instead of invalid signatures, covering a large number of record sets, for instance, any type responses. And also attacks covering different record sets conforming to whatever protocol semantics, you name it. That is because the fundamental problem which was exposed by KeyTrap is that CPU resource exhaustion was never properly addressed in DNSSEC. There are some exceptions to this. You can look them up afterwards. I'll skip through them in the interest of time. So in conclusion, the short-term fixes against KeyTrap address all the attack vectors, but introduce themselves so far unmanaged complexity. The countermeasures fall in two kinds, two types. So first is architectural containment, namely scheduling-based countermeasures, which is intermitting long-running validations to allow other tasks in the pipeline to proceed. If you're doing just that, you still allow an attacker to pin your CPU and thereby waste, albeit low-priority CPU cycles, but still not desirable. The other class is limits, namely limiting cryptographic operations. There's a number of them. Signatures try to validate a given record set, keys tried with a given signature, and so forth. Most importantly, there's limits on the signatures and DS validations per resolution, which extends the limits imposed by the DNS, plain DNS specification from the earlier RFCs to DNSSEC. Let's focus at them for a moment, because they themselves are probably the best way to approach the problem, but also come with their own drawbacks. So at the moment, these limits and the values are hard-coded or set in a configuration file, which is desirable and arguably necessary because you have different deployments which you have to consider, which have different capacities, different use cases. But it's also problematic in the absence of a mechanism to actually signal these limits. So at the name server side, you don't know whether a resolution failed because the validation budget was depleted or something. It's just something which is observable on the resolver side of things. Thus, it introduces a factor of unreliability for the domain operators, which is a disincentive for them. Yes, I think most of us know that on the domain side, things in DNSSEC don't look too bright to begin with. So also these per resolution limits introduce dependencies from DNS to DNSSEC, something which we say constitutes a layer violation, and that restricts scalability of the DNS in many dimensions and hampers future DNS protocol development. So managing the validation complexity in the face of these per resolution limits is pretty challenging. Complexity in two senses. First, validation complexity at the validator, but also management of this complexity, namely in the terms of validation budgets. Let's have a look at some of these factors. First, there's the number of record sets requiring validation in responses, which can vary a lot. So imagine we are introducing additional record times, for instance, DELEC, that would effectively double the validation complexity of the delegation chain. There's also something we call elective validation, an effect of scrubbing. You can see on this slide here, here's a response from a well-managed domain, MX response, which carries 8 signatures. Only seven of them are optional to validate. Only one of them needs to be validated to actually get the response answered. And also, we could consider future DNS use cases which are hampered by this. Just because DNS is open, you don't want to. You need to consider every aspect in which DNS is going to develop. If you introduce new record types, you also introduce additional validation complexity if you don't pay enough attention. Then there's key-tag collisions, which induce natural validation failures, so cryptographic mathematical validation failures, not failures because a signature has expired or something like that. And these make validation complexity a matter of probability, because if you allow for them, you cannot 100% exclude that they don't happen, right? So these tags don't necessarily follow a uniform random distribution, which is known knowledge, has been seen before. Here, an example with RSA, which neglects half of the key tag space, depending on the public exponent chosen, but it can be even worse than that. And in the end, collision probability depends also on the DNSSEC algorithm chosen, if future DNSSEC algorithms don't work against that. So there's additional factors, for instance, crypto agility. Future algorithms might increase CPU load, or even change of crypto libraries might increase CPU requirements, which need to be considered, and additional promoters of complexity, which I'll skip over in the interest of time. So we are essentially proposing 2 long-term solutions, quickly summarized as first management of validation budgets. So we propose to set a global minimum per resolution validation budget in the specification, which does not consider elective validations, which I showed you earlier, or caching. And these should reflect current operational insights and get updated over time. And this then would allow these interzone budget alignment, which I talked about earlier. Then we'd propose to introduce also EDNS options to signal the total and current validation budget from resolvers to name servers, and EDNS error code to signal the validation budget depletion from resolvers to clients. This would enable to support global monitoring of validation budget at the domain side, but also at internet nodes. Second, we propose to outlaw key tag collisions, because just demanding key tags to uniquely identify a DNS key in a zone would be first a blunt confrontation to current specification, and just changing the semantics of the current records would also require worldwide coordination, which is hard to enforce without breaking things. As a solution to this, there are actually two approaches. One is a proposal of ours, which is introduction of a new record type, which we call ID key. More about that in our publication. And also another proposal by Mark Andrews, which would be a new DNSSEC algorithm semantics. So if you do, it would be introducing new algorithm numbers, allocating them for new or existing algorithms, and if a resolver or validator encounters such an algorithm, it needs to enforce this uniqueness requirement. Okay, that's about it. Thank you for your attention, and here's a list of our publications if you want to look up more details. Thank you.
Thank you very much. The next and last speaker in the presentation part of this discussion panel will be Yehuda Afek, showing that you don't need DNSSEC to attack CPU and memory. Please go on.
Okay. So thanks a lot. It's a presentation prepared together with Anat. Basically, my talk will go through several vulnerabilities. I will first explain the relation to high availability and fault tolerance of the DNS system, and then we'll do a cycle between vulnerability, mitigation, vulnerability, mitigation very quickly. So first, the high availability. One of the key elements to ensure high availability in the DNS is to allow large delegation responses that contain a number of name servers and many other resource records to support the high availability. And when you resolve all of them, because you want to know which one is the fastest, the quickest to respond, you create a lot of traffic. And we'll see it in the next NXNS attack that we discovered in 2019. And the attacker owns both a client and an authoritative server. And you can see now the zone file of the authoritative server inside this block. You see a lot of non-existing names. So this attack using the NX, the non-existing domain names for the name servers. It tries to resolve all of them, creating a huge attack per one query. And if you have many botnets, like in the Mirai attack or other attacks, you get a gigantic attack, easily killing any resolver, and you have many different combinations to kill different authoritative servers as well. Mitigations, we have suggested several different mitigations together with the people from North, Unbound, and Bind. But in the end, the one chosen, when you get a large referral response, only resolves the first 5. So that was adopted by the different vendors. And if none of them result with a resolution, go to the next 5 and the next 5 and so forth. So let's see how this mitigation results in another attack, which is the non-responsive delegation attack. What we did here, it's the hot code is the mitigation of the NXNS. Now we create again a large response with a large referral response with 1,500 different names. And turns out that each resolver, when it receives such a large list, it checks each of the names in its cache and its database memory. So it results in 3,000 lookups in the memory. But by the NXNS resolution mitigation, we say you only resolve 5. So you resolve 5 of them, and none of them reveals the name, because now we put in the zone file of the authoritative, the non-responsive referral, non-responsive names. So none of them give you a name. You resolve another 5. Each of the first 5 generated again 1,500 new names that you have to resolve. So you get now 25 packets, each of them with 1,500 that you have to look up in your memory and in your cache, and so forth. Another round, and each of the 25 gets to 125. And you can see the count of the machine instruction in the resolver goes up by 10,000, 10 to the fourth, the number of machine instruction for a benign query. And you can see most of all of the resolvers we checked were affected, and their performance degraded considerably. The mitigation for this attack, so now we are in the second loop from the first slide. Okay, don't look and don't validate more than the first 20 names in a large referral response. That's what you do for your mitigation. Okay, and that really took down, if it's a normal performance, under attack you see the red bars, and with the mitigation we go up about 90% of the normal performance of the attack. When we look only at 20, you don't do 3,000 lookups, you do only 40 lookups per large referral response. And then we thought, okay, so what is still missing? The attack on the cache. In NXNS, we said resolve 5 at a time. Then you said, don't ignore anything beyond the first 20. But the resolver still kept all the 15,000 records, resource records, in the cache. So that's what we did. And this attack, simply you have a benign request, and very quickly we send a packet with 15,000 and several packets with several zombies, and we flush the cache. We simply put the cache a lot of data at a high frequency, and you can see that whatever you do, the packets are coming very fast, and we can flash the cache. Interestingly enough, the one resolver, the not resolver, was not affected by this attack. So I believe they are treating the cache differently. So what we do to resolve this one, the different people that are here, you know better than me, they suggested, okay, you don't completely ignore, don't put in cache, don't do anything, chop off and take only the first 100, actually any resource record, because parallel to our attack, the Elias attack, the KeyTrap attack, so they said also don't resolve more than 10 lookups per packet. And you can see, to summarize what we've seen, since 2019, until 2019, you can send a huge referral response. It's really the key engine for the amplification factors in all the different attacks. The key engine for the amplification is this huge referral response. There might be other good engines, but it's the one we are working on since 2020. And you saw that we restricted to 5, then to 20 at most to treat, and then completely ignore anything beyond 100. So the key question that for me, I'm not an expert, maybe people here can tell me what should be the maximum number of name servers or any other resource records in a referral response. Should be 100. So here we took what are the number of name server names in, you're trying to serve the top 1 million domain names on the internet, and we observed that most of them are using 2. You see on the x-axis is the number of name servers in a resolution response, and on the y-axis, the millions of I mean, less than millions, 0.600,000 name servers. When you resolve them, they have in the referral response at most 2 names. And you will see there are few with 13, and then we listed all the ones from 13 up to 60. There was one guy for whose resolution there was a 60 name server names. So what should be the maximum? So then we tested, these tests are actually from a week ago, from the 17th of October, that we probed the different resolvers to get the numbers. And we tested only TLDs. What are the root supplies large referral response for the TLDs, because that's very critical for high availability and fault tolerance of the system. And we saw that 6 is a popular number. None of them is beyond 13, and the number of TLDs that use more 13 is 0.2%, very small number, about 3 of them. So maybe the maximum number should be 13. I don't know, I'm newcomer here, it's my first time, but it's something that I think you should try to bound and constrain this explosive machine of the referral response to a small number. And for not just for name servers, for any resource record, as Elias showed us, for cryptographic keys, for DNSSEC keys, for A records, for other type of C names and so forth, because each of the attacks I showed one variation, but we had variations with C names and with other mechanisms to make the attack effective. So we saw first communication complexity attacks with large packet amplification factor, then complexity, the NR delegation, and also the KeyTrap that Elias showed in parallel to our work also is using this large referral response with many keys. And the last attack that I showed you is the one that can flash the cache again and again. And conclusion, we need a thorough analysis of the resolver complexities, both the CPU complexity, the communication complexities, the memory complexity, and so forth. And we need the good QA. I don't know if maybe you know the work much better than me, but somehow to test all the different resolvers implementation, maybe a shared lab of ORC or something else to test the different implementation to be able to quickly identify the weak spots, likely with collaboration with the academia, using automatic things for verification. We've seen some works of this. We can learn a lot from software engineering because it's very similar to buffer overflows and to counters running out of control in different software programs. Thank you very much, and will be a question that will be next. Thank you.
Thank you to all the speakers. And I invite the speakers back on stage, because now we will get to the discussion part where we have 20 minutes where we can together, speakers and you from the audience and also remote participants can ask questions, and not only questions, but also remarks about the research, what you are missing, what you found out very interesting, and so on and so on. Really up to you what you want to ask. Thank you, our presenters. Just to sum it up, we've seen here on stage that basically these gentlemen managed to attack all the aspects there are to be attacked, like the network, CPU, memory, using all different aspects available, and that includes timing of the queries, source addresses, the indirection in the DNS, DNSSEC data, or just simply size of the thing, the RR record. So there is so many things which can go wrong, but the question is, what can we do about it? But Jan, I can see that you are waiting to pose your question. Go on.
Yeah, I'm waiting. Can I ask questions? Or
of course,
yeah. Thank you for great presentations. It was really interesting. And there's one thing that there was like overlap between two presentations that I found interesting, and that's the self-amplification and maybe the resource limit in the eDNS. There is like one thing that I think might be missing in that self-amplification, and it may be because it's not part of the DNS protocol, but a lot of DNS vendors do it, and that's like self-references or cycles in aliases, in alias records. So alias records are not part of the DNS specification, but are basically needed. Vendors implement it, like it's custom implemented. There are different names for it, but it's basically like a CNAME that's usually put into the zone apex, where the CNAME normally cannot exist. And the authoritative server, when it receives a query for that CNAME, it basically synthesizes A or quad A record. And to get that record, it has to talk to the resolver. And if you set up, you can do it probably with one provider as well, but you can do it with multiple. You can build like a chain of these alias records that point to each other. And the problem with that is that you cannot easily break that cycle because there is not, the resolver doesn't see the individual names. They're like hidden. The authoritative DNS server doesn't give out the answer, like the target of that alias record. So if you send if the authoritative server then receives this query for this record that is part of the cycle, you will start seeing like the queries bouncing between the resolvers that the authoritative servers use, and it's difficult to break the cycle. What breaks that cycle eventually is that one resolver will receive the query a few times, and because it's like duplicate query, it will just stop processing the second one and waits. But it involves times out, so all the resolvers try to start retrying the queries, and it creates like this amplification spike. Somebody commented on the Meeus that communicating the limits in eDNS might not be a good idea. I think in this particular case, it would fix the issue if we could just like include some information into eDNS and say like identify the cycle somehow and be able to break it early.
Thank you for the comment. I will offer mic to our presenters on stage. If you want to react, just wave or...
Just a quick note that we've seen such an attack published by people from New Zealand, I think. And there's a work by people from UCLA, Siva and George Varghese, who do verification on the zone files. If you collect it, not, as you mentioned, you need more than one zone file because you can loop between two or more zone files. But if you analyze in a simple verification method the different zone files, you can detect those cycles and take a note of them and kill them.
Yeah, maybe also another comment on this point. So I think in general, it would be helpful to for the resolvers to implement some kind of anonymity detection mechanism, right? They just keep monitoring is there any like anonymous query pattern and like a circle, like a loop, or like a very large amplification, sort of things like that. Then that would definitely help to also detect and mitigate this kind of attacks in general as a generic mechanism. Yeah.
Mm-hmm. Thanks. Kathy, go ahead.
Kathy Almond, ISC. I was interested, it was fairly early on, there was a discussion of the way that attacks on DNS are either attacks on the DNS service itself or DNS is being used as a reflection. There has been an upsurge in reports, I think, of obscure ways of implementing a way of getting DNS to mount an attack on someone else, reflections. But these seem to be increasingly obscure. I'm wondering if the researchers have seen the more obscure ways of implementing DNS as a reflector actually used in practice.
Maybe I will pose the question for Richard, because really from the industry, have you witnessed any of what we've discussed in practice, or is it just mostly bots sending NX domain queries?
Yeah, so far most of it has been from bots or scripted tools. I'll be very interested to sort of hear what sort of other assets you're hearing about doing these different types of attacks. But
I'm not seeing. I'm not in the business of getting data on actually seeing reflection attacks implemented. I'm interested in the fact that we get reports of if we do this with, if we mount this particular setup, then we can induce the resolvers to cause a reflection attack on a third party. And I'm wondering if this is actually happening in practice per the increasingly obscure designs of ways of getting DNS to do this.
yeah, I haven't seen it. Generally, the reflection techniques seem to be sort of fairly standard over what we've seen for the last few years. There's various things like padding out the DNS to generate very large queries. Generally, the challenges for the attackers is they want to get the biggest amount from the amplification factor. So the small query to the large payload, that's where the challenge is to try and get that as large as possible. So they require the fewest amount of original queries to generate the largest amount of payload. But in terms of sort of novel techniques outside of the standard,
for example, setting up servers that behave in a certain way and then inducing clients to query those servers, do you see that kind of thing happening?
Do you mean having people actually setting up their own recursive DNS servers?
No, more like seeing people setting up authoritative servers with particular characteristics in the way they respond per, say, DNS-bomb. Have you seen that being implemented?
The DNS-bomb is something that we've seen that as an attack vector, but it's not something that we've seen as a reflection tool.
Yeah.
Thank you very much. Please go ahead.
Hi, Jeff from Microsoft. I had two questions or comments. You asked us to bring up things we thought were notable, but I'd love to hear thoughts. One on the message amplification, it was mentioned, I think, that there was one scenario where you could get a factor of almost 8,000, and I was just curious to learn maybe what that was. And the other was, for DNS-bomb, it seems to me like an interesting thing is detection is difficult, and I was just wondering if you had any thoughts on how a typical DDoS platform might detect that in a way that currently is not able to.
Okay, thank you for the question. I guess that
yeah, maybe I can go first. So basically, that number means like we send from the client's point of view, we just send one request to the resolver, and it would just keep generating queries by talking to our specially configured name server, and eventually it will send up to around 8,000 queries in total. Yeah. And that's basically the definition we have for message amplification factor. And the reason why we can go that high is because like we compose of the different features, and there's they can kind of bypass some of the limits of resolvers limits on individual features, and then eventually get adapted or get multiplied. So that's how it was produced. Yeah.
Yeah, I was surprised that resolvers wouldn't have built-in protections, and I was just surprised that you were able to get up to 8,000. So maybe I'll follow up offline and find more about the specifics.
Yeah, definitely. Actually, we have been working on improving our test bed, and then I guess we can maybe do some even live demo or something after that. You can, yeah.
Cool.
I will add to that answer point of view of the implementer, because we in Bind, we of course have the protections which limit certain things, actions to given limits. But the trouble is that these gentlemen are very good at defining corner cases where their limit get accidentally reset and then it goes on again and again and again. So it's not the lack of limit, it's like holes in the enforcing the limits, so to say. Okay, yeah. Benno, go ahead.
Hi, Benno Overeiner in Knowledge Labs, implementer of Unbound, and a very effective amplifier of many things. So thank you for your work. And also, I also kind of the word to the room. We all coordinated these vulnerability disclosures with, the OARC platform, with MetaMost. So this, so OARC also provided this trusted environment to share vulnerabilities. And I think four of us, so also the remote speaker, we worked very well together with ISC, with CZNIC, PowerDNS, and all the other implementers. So again, thank you for coordinating this and helping us. maybe I should put that at the very end, but I hope you're done, but probably not, you're researchers. So I have actually 2 questions for you, but I think everyone else can join in. For Yehuda, you mentioned one thing, do we need a platform for testing software? Of course, all the software developers, they have their unit tests, et cetera, before they release. The thing is, and maybe I insult some people, but software engineers, we do our utmost best to write software without problems. And as Petr just mentioned, yeah, this enforcing of these limits, we know there are some limits, but I think security engineers or security researchers, they're different kind. They think differently about breaking things, and we are working things. So I hope I don't insult too many people, but just providing a platform to test software is probably not sufficient. I think we need the security researchers involved because they want to break stuff, and they're independent. How to say that? We are looking. It's our child, so it's difficult to hurt our child. So that part, maybe you have some comments. And you also said about the formal verification. I hope universities, academic, will pick up on that. And because I think that can give us insight on all these limitations on recursions, counters, cyclic, Elias, C names, whatever. Much better, it gives us some predictive way to pinpoint vulnerabilities, and we can implement these limits. So this is a little bit a question to all of you, but it was a very long question. But I hope you can react on that.
No, thanks a lot for collaborating with us on the disclosure procedures several times. I don't know, I'm just first time here, but if there would be a good setup of a lab in the cloud with the different resolver, with different vendors, where also academia, if you will need to do some verification who is doing the test, but we ask your permission, maybe members of OARC, and we then can play, we have a playground where we can do the attacks, we can do, today there are many of the attacks, we cannot test them on open resolvers, of course, or on, so if the other vendors like Cloudflare and Google will also collaborate, we will be able to mount attacks. I want to test my attack on, so I can download the Unbound or Bind or not and implement it in my lab. But for example, for Cloudflare or Google and the other open resolvers, I don't have their software. They don't put it in some sandbox, cloud sandbox where I can test and tell them, hey, you are also vulnerable or you're not vulnerable. That would be very helpful so we can collaborate. Besides, I think good QA people will, you know, they poke different things and they will also test what security people test. We find vulnerabilities, it's kind of security, but it's not a genius security or very deep knowledge about cryptography or something. You test which things are unbounded, which things has a lot of potential, and we just, you know, you play with different variations, boom, you get a variation that, oh, it's explosive, and you have an attack. So I don't know, I don't know, but I think good QA, and if we share, I don't know if you share among all of you the potential for a cloud sandbox to test those things, it will be very productive for the, and verification is difficult, you know, the formal verification, it's we are trying it, I talked with George Verghese and other people from UCLA and Microsoft, but it's a tough question. We are trying to do something more with the large language models to see how, but that's a long way to go and we are working on it.
Excellent, thank you very much. And maybe something for OARC to explore how we can work together into the platform.
Maybe just a very, very quick comment, like actually in terms of formal verification, that's also something formal verification and formalization of DNS. That's also something we have been working for a while. And I think I fully agree that it's really a very challenging task, because just in terms of formalizing DNS itself is already very, very challenging, very difficult. But and also it's very, from our perspective, it's really important to understand what industry, what people like you care about, like what kind of properties we care about, whether it's kind of correctness property, functional properties, or security properties, what kind of things. So and in terms of this, that collaboration between like academia and industry will really help us to push this forward. Yeah.
Thank you. I believe we have a question from a remote participant, right?
A comment from Prof. Weber, Akamai, say regarding referral limits, another vector to consider that in referral you have a name that can have a lot of IPs. If we limit, we need to consider this also for litigation. In the end, resolvers care about name server's IP.
Thank you for the comment, Ralph. Greg, please go ahead.
Greg Choules, ISC. I hear a lot of good stuff going on here. I think it does need to be formalized, as you were saying. There needs to be a sort of global formal acceptance process, but I think the outcome of that needs to be fed back into the standards bodies. And I think DNS has to kind of grow up a little bit. It's started life as being, have as many as you like, and that has been the cause of a lot of recent problems, like the number of NS returned and things like that. And so it's going to have to be mandated that at some point there is a limit, and if you don't adhere to this limit, then your domain just doesn't work anymore. And so then, because there is a limit in the standards, resolver operators can genuinely say, no, I'm just not going to do anything with your zone, go away until you fix your zone. But we're going to have to do things like that, because if it's not formalized, then we don't have it's there in the standards, you must abide by it, otherwise you can't play in the world anymore. At the moment, it feels like it's all a little bit reactive and based on feeling, and how does my particular software work? Is this a good number for me versus somebody else? And it's, we need to get to a point of that is the number. So we don't get 60 NSs anymore. There's no need. Thank you.
Thank you for hinting at it. The common theme of all the research was basically limits of various sorts of different resources available. And because we are slowly, rather quickly running out of time, I will prime you with the question what the limits should be. That can be discussed over lunch as well, because there is so many things which can go wrong in DNS. And is it reasonable to set hard-coded limits in standard, as Greg just proposed, and feed it back to the standards bodies? Or do we need to be more like future-proof and then have some sort of like gentleman's agreement that, okay, current versions will enforce limit of, 10 CNAMEs in a chain, but in the future it might change? Should it baked in the standard, or should it be, just set by the developers at the time because it reflects the current situation on the world internet, and it will evolve in like 2 years because the operation needs have changed? Or what do we do? Where do we go from here? So I hope that this will serve as a thought for your thought, and we can discuss that over lunch and over the course of the weekend. Unfortunately, we are out of time for this discussion panel. So I have to thank all the speakers. Thank you very much for taking the challenge and co-presenting. It's unusual format. I'm very grateful that you were up to it. And also thanks to VeriSign, who is 2024 workshops patron. Thank you to CZNIC, NetNode, ISC, and Verkara for being OARC 43 patrons. And now it's lunchtime.